Okay, welcome back to Feedback Control Systems. This is Module 10.3, Introduction to Frequency Response. The objectives of this module are to look at a frequency response concept, so to conceptually introduce this topic, look at some analytical expressions for frequency response, and then finally look at the frequency response of a transfer function. So first, an introduction to the frequency response concept. We have previously looked at moving from the time domain to the phasor domain as shown here. So we might have some cosine term or any sort of sinusoidal term, has a magnitude, so sort of the peak of the sine wave, m1, and it has a frequency omega. Again, that frequency omega is 2 pi f if you have f in frequency in hertz. And then a phase shift relative to that. So relative to, say, a zero reference, you may have phase. So from a phasor domain, what we did is we simply just take the magnitude and the phase angle, and we assume that we're operating at one and only one frequency. So we're just focused on the magnitude and phase. Now, as we look at an example, here's a mechanical translational system, mass spring damper system. And if we now look at our position here, as a function of a forcing function, but instead of a constant force, now we might have a sinusoidal force, right? So on that mass, we might be moving that force at a sinusoidal waveform, and so that position is going to be moving, and so we want to be able to track that position as a function of this forcing function. So this force may have an input magnitude, the position will have an output magnitude. Notice they're at the same frequency. And it looks like this got missing a T right there. So they're both at the same frequency omega. And they each have a phase. So the input has a certain phase. The output has a second phase relative to that. Okay? So we could put this representation in terms of phasors, looking at the block diagram. So I have taking the input function right here. I have an input magnitude and angle, so that's from our forcing function. And then this would represent our mass spring damper system. That would have some magnitude and phase associated with that as well. And then we have some output characteristic where we find the output magnitude and phase relative to that. So when I do this multiplication, I can find here's my output equals to my input magnitude. So what do I do with phasors? I multiply the magnitudes and I add the phases, right? I multiply the magnitudes and I add the phases. So that's how I would get my output response. I could then translate that back into the time domain. So if this is my forcing function, magnitude mi, and a phase shift of theta I there, that's my input. And then relative to what my position's doing, here I could find my output magnitude if I knew the magnitude at a given frequency of that transfer characteristic. I just multiply those two, so mi times m would be my output magnitude, and then the phase angle right here would be my initial plus the phase associated with that transfer characteristic. So I can do the analysis in the phasor domain, and then when I'm done, translate that back into the time domain quite simply by showing what my plots would look like. And again, what we'll see, we saw that on the curve here, is that the magnitude relationship here of the transfer function is really the output over the input magnitude, and the phase characteristic of the transfer function, the plant if you will, it's the difference, the output minus the input in terms of the phase. Okay? Now what we want to do is switch and look at some analytical expressions for the frequency response. So here what I have is a plant. Now notice my input R of S here. My input R of S is now, doesn't look like a step or ramp, it's actually a sinusoidal. So if you go back, look at the Laplace tables for a sinusoidal input, you're going to see this characteristic right here. So this is from Laplace. And then what you'll see in terms of our output CS is that input right here. Our input times our plant transfer characteristic. So the general form of that solution, we can use partial fraction expansion and find two terms, K1, K2, and then essentially solve this. So the approach to solving this from our partial fraction expansion, not going to go through all the details with this for you, but basically do that substitution as we had seen previously. So what we're going to do is we're going to first, for the K1 term, we want to isolate that term, and so we want to substitute in the s of minus j omega for that term, and then to find the k2 term, we want to do this cross multiplication here, and we'll substitute s equals plus j omega. Okay, so that's a reminder from our partial fraction example, worked examples. And then as we go through a little bit of math here, but when we're done here, we can see sort of our end response for both K1 and K2. And what we'll see here is that K2 comes out to be the complex conjugate of K1. Okay? And so what we can do, we can tie all this up and look at the magnitude here, magnitude of this transfer characteristic as a function of frequency. So we can have a magnitude and a phase by looking at the magnitude or the angle of that characteristic as s approaches j omega. So we can actually look at this in the frequency domain, okay? And then what we can find for our C, our output in the steady state, is basically do the substitution of this down here, okay? So we basically put in our K1 and our K1 complex conjugate terms in there, okay, over their appropriate terms, and then we can do a Laplace inverse to get from the S domain back into the time domain, and we get this characteristic that we see right here. Okay, and what we'll see here is that the output, if we kind of break this down, is it's a function of the magnitude right here, the magnitude of the input, right? The magnitude of the input and the magnitude of this transfer characteristic equals the magnitude of the output, just like we saw in the phasor domain, and then the phase shift between the input and the transfer characteristic. So we multiply the magnitudes, we add the phases. So this is sort of the analytical proof of what we saw essentially on the previous slide. I'd say, certainly go through this, look at this, but the key takeaways is if you think about it in the phasor domain, I think it's a little bit more straightforward. Now let's look at the frequency response from our transfer function. So let's first find the magnitude phase expressions and then plot. So let's assume I have a GS right here, 1 over s plus 2, and then don't forget, in this case, s is going to be j omega. So what we're going to do is substitute that in, and you'll see the substitution. Now here, what I want to do is not have a term in the denominator that is complex. So I'm going to multiply this by its complex conjugate and get this term right here. So let's maybe do that out real quick. So I start with 1 over j omega plus 2. This is what I have. So I don't like to leave a complex in the denominator, so I'm going to multiply this by 1, and so I'm going to multiply by its complex conjugate, which is negative j omega plus 2 over negative j omega plus 2. So I'm taking this original, multiplying it by 1. And so what we're left with in the numerator is just 2 minus j omega. That's what you see, minus j omega. And then the denominator, what we'll have is I'll walk you through it. So I have j omega times j omega. It's j squared, but I have a negative. So negative j squared omega. And then I have a negative 2j omega and a plus 2j omega. So those terms cancel, and then I'm left with plus 4. Okay? So I'm left with that. However, well, I still have a j, but what is j squared? J squared, let's go back to our complex plane. This is our real axis here, which I'll just call sort of 1. This was our plus j term. This is our minus j term. So what happens if you're trying to find these j terms, you can think of this, instead of 1, think of this as j to the 0 power. And then if I have j, what happens is I start to rotate this way in a positive direction. So this j is really j to the 1. This j squared is here, and what does this look like? That kind of looks like negative 1. And then this is really j3. So it's j times j squared, which is the negative. So you can think of that as negative j, and then so on and so forth. So j squared I can replace with a -1, so those two negatives cancel, and then this turns out to be 2 minus j omega over omega, oh, but I forgot to square the omega, right? Sorry about that. J omega times j omega, there's an omega squared, and I'm left with an omega squared plus 4, which is what I have shown on the slide. Okay? So I just wanted to walk you through how we went through that. You multiply by 1, and you multiply by its complex conjugate, y. So eventually, when I have this j squared term, I'm left with no imaginary part in the denominator. So now what I can do is calculate the magnitude of this, and when I look at calculating the magnitude of this, you'll see I have this expression right here, and I'm left with 1 over omega squared plus 4, and then I can do the phase. The phase angle of this is essentially the inverse tangent of the imaginary part over the real part. Okay, so we've seen this before. Now what I could do is find the magnitude of the system, but one thing so we found the magnitude, but one thing we will do often is we'll plot the magnitude in decibels. And so what we can do is take this magnitude as a function of frequency as shown here, take the log of it and then multiply by 20. And this log is log base 10, just to be clear. So when we take the log of that, multiply by 20, we can express that in dB. And so we can see that attenuation, if you will, or gain, depending on how we look at it, of our system. So if we have like we're trying to attenuate something by a factor of 1,000 or hundreds or something like that, sometimes dB is a little bit better way to express that. So what I'm showing here are the magnitude and phase plots. So this magnitude plot, 20 log of m, so I'm actually showing this in dB. And so when I plot this characteristic here, what we can do is find, for example, at a variety of frequencies here, the frequency here is in radians per second because I'm using omega here. And then, I could substitute in various values. So if I substitute in omega equals 1, I should get that point. So 1 squared plus 4 square root of 5, 1 over square root of 5, I would get this magnitude, and then 20 log of that value, and I should get a value close to, looks like about minus 7 dB here. Then what I could do for the phase is I could look at the phase at that same point, and then calculate that. If I use omega of 1, the inverse tangent of 0.5, in terms of phase, I'm showing here in degrees, I should get the phase, it looks like roughly minus 25 degrees or so right there. So you can use these expressions to calculate any points that you have in your magnitude or phase plot, and then eventually make a whole plot here. Now MATLAB will have tools. We'll show you how to use those tools. So once you have a transfer function as shown here, it'll do that work for you. But it's good to see it and be able to do a few examples by yourself. Now this plot right here does a little bit different view. As I look at G as a function of j omega here, what it does is I first look at the real part of G and then the imaginary part of G. And so this is looking at my omega in terms of radians per second. So what this plot does is, again, as I make some changes here, you'll see, depending what the real part is and the imaginary part here, what the actual frequency would be in terms of radians per second. So you can see it starts at 0 radians per second here, and then it starts to increase to 2 radians per second here when the real and imaginary parts are essentially equal in magnitude, and then it continues and it grows with frequency as we go here. And so what's happening? The real part is getting smaller. Okay, the real part is getting smaller, and then the imaginary part getting smaller as well as the frequency starts to increase more and more. Okay, so this is just an alternative way to look at it. We're going to be generally working on these magnitude and phase plots right here. And again, one thing I want to say is the frequency we normally put here. You'll see this is on a log plot. We'll put it on a log so we can sweep a wide range of frequencies here and be able to see some response and characteristics. So this This module serves as an introduction to how we'll look at transfer functions here in the frequency domain, plot, magnitude, and phase. And then what we're going to do in upcoming modules is use this to look at doing compensation in the frequency domain, using these plots instead of root locus to design things, again, directly in the frequency domain. So more on that with the upcoming modules. If you have any questions on any of this material, please don't hesitate to reach out. Thank you.